Welcome my friends, welcome to my next lecture. Now in my last lecture I was talking about what is called Cauchy's integral formula and Cauchy's integral formula for derivatives. And you have seen that many problems like calculating contour integrations, instead of using the definitions of contour integrations, even though if you know the parameterizations of your contour, using Cauchy formula or Cauchy's integral formula or Cauchy's integral formula for derivatives, you will be able to calculate those integrations very nicely. Okay, so that is one of the advantage. Now today I will talk about as an applications of Cauchy's theorem or Cauchy's integral formula or integral formula for derivatives, couple of nice theorem like Cauchy's estimate and Liouville's theorem, one of the beautiful theorem in complex analysis. So, and if time permits, I will talk, maybe I think in my next week I will move this discussions about Morera's theorem, not for this week. Just let me see whether I will be able to finish what is called Cauchy's estimate and maybe the statement of the Liouville's theorem. Okay, so as I said, so let me just see couple of beautiful consequences or applications of Cauchy's integral formula or Cauchy's integral formula for nth derivative. One of the beautiful application, if you see, you will see this is the one. So as I said, so this is very powerful. I said that analyticity implies infinitely many times differentiable, right? And actually that is the consequence of Cauchy's integral formula for nth derivatives, right? So look, the theorem I am saying, suppose I am starting with a open set D. If a function f is analytic in D, then for each n the nth derivative fn of f exists, and this is also analytic. Okay, so in fact one can prove this theorem using Cauchy's integral formula. By Cauchy's integral formula for derivatives, the above theorem follows. So that means what? That means Cauchy's integral formula, what if you just recall the definitions of Cauchy's integral formula for nth derivatives, you will see the analyticity on a simply connected domain is given. So suppose your domain is nice, then Cauchy's integral formula for nth derivative says that if I take a point which is interior to a simple closed contour C, say positively oriented, then I can have or I can write the nth derivative of f. Of course, first you have to conclude that yes, your function is n times differentiable. Not only that, I have the expressions of the nth derivative of f at some point of z0 in terms of contour indications. And in terms of contour indication means what? If I know the value of the functions on the contour, I can have the value of the nth derivative of f at z0. As long as my z0 is sitting or interior to C. Now if I have interior to C, there are many points. So many points you have the value of nth derivative of f at that point, and that means that nth derivative exists, and that means all other derivatives n is actually running from natural number, then my function is infinitely many times differentiable. So therefore I didn't have to prove it explicitly, but if you understand what is called Cauchy's integral formula for nth derivative, in fact this theorem follows as a consequence of that. If I have a domain open set, if my function is analytic, then my function is n times differentiable, derivative exists, and not only that, each derivative is also analytic, but that is also infinitely many times differentiable. Okay. So this is the theorem. So this is, as I said, it's a very powerful theorem. This kind of theorems, you cannot have it in real analysis. So-called, if I say that if I just somehow compare the analyticity replaced by differentiability, there you will have plenty of examples of functions where my function is one or two times differentiable, but not 3 times, and so on and so forth. So as a corollary, you can have it. Let D be an open set in C. So suppose you have a function f which is of the form u plus iv, which is analytic. Then the component functions u and v have continuous partial derivatives of all orders. Well, it is also clear from the statement. Now if f is analytic, that means what? U and v first order partial derivative will exist and they are continuous, right? So that I know by sufficient conditions for differentiability. Now if f is analytic, implies f is infinitely many times differentiable and all derivative also analytic. So therefore you can write f prime is ux plus ivx. Now this is analytic. That means each first component is ux, second component is vx. That means the partial derivative of ux and partial derivative of vx, there also exists continuous. But what is the partial derivative of us? That means you have uxx, uyx, vxx, vyx, or vxy, whatever it is. Okay, so all second order partial derivatives of u and v, they exist and they are continuous. Now then go to f double prime, that also you can write is uxx plus I vxx. Again f double prime, it is also analytic. Then again you use that say that the real part of f double prime and imaginary part of f double prime, they are also all order partial derivative of exist and they are continuous, and it will implies that all order partial derivatives of u and v there exist and they are continuous. So actually it follows from the above theorem. Since f is analyticity implies all order derivative exist and they are also analytic. And each time you have the expressions of f prime, f double prime, f triple prime, then you have the existence of all order partial derivative exist and they are continuous. Okay. So this is this theorem, and corollary it actually follows from what is called Cauchy's integral formula for derivatives. Okay. So now again, as a consequence, you will have what is called Cauchy's estimate. What is Cauchy's estimate? Again, you will see it says that this is the statement. Proof actually follows again using the contour integrations. What is that? Let fz be analytic on and inside what is the circle. What is the circle? This circle, if I draw it, this is a point z0. This is a circle of center z0, radius r. So this is r. Okay. So this is circle center z0, radius r. So if I have a functions analytic which is analytic on and inside my this domain, this is my domain, okay, and suppose m is the maximum of modulus of fz if z runs over this circle. This kind of argument I have already discussed. Since my function is analytic on and inside, so therefore it is continuous on the contour, and since it is continuous and contour is compact set, so therefore your maximum will always exist. Once I have that one, then Cauchy's estimate says that I can estimate the nth derivative of f at z0, which is dominated by factorial n times m divided by r to the power n. Factorial n, of course I am dealing with n, so therefore factorial n is there. What is my m? Is the maximum of my function's modulus of fz on the contour, and what is my r? R is the radius of the circle. The circle means the circle I am dealing with, z minus z0 is r. So therefore you have this estimate in terms of m, r and factorial n. And you will see this actually follows from the expressions of the nth derivative of f at z0 I can write in terms of contour integrations. So proof is very nice. By applying Cauchy's integral formula for nth derivatives, because you see f is analytic on and inside the circle. So therefore since it is on and inside the circle, so therefore the domain you can have it little bit about the circle. So therefore I can draw the picture. So this is the point z0. So this is my z minus z0 is exactly equal to r. So now you see, so you can have, maybe you can say that this little expand from your circle, because I need a domain where my function should be analytic, and inside that domain that should be a simple closed contour, z0 sitting inside, then I can apply Cauchy's integral formula for nth derivative. So if I do that one, so since my function is analytic on C, so therefore you can have small expansion around where my function is also analytic. And if I consider this is my domain where my contour C is z minus z0 is r, on that contour which is sitting inside my domain, z0 is interior, and therefore I can apply what is called Cauchy's integral formula for nth derivatives. So I can write the expressions of nth derivative of f at z0, which is factorial n divided by twice pi I, fz divided by z minus z0 to the power n plus 1 times dz. So I have the expressions. Now I want to estimate, so what you have to do? You have to take the absolute, and again the standard trick, you have to use ML formula. That's it. Or you can change contour integrations, use the definition of contour integrations, you can have the estimate. This is straightforward. So if I have this absolute, so if do not kind of care about this object for the timing, because this is exactly you can push inside your modulus inside the integrand. So this is okay, this is okay. You may scared about what is modulus of dz. So do not worry about that. Okay. So what you will do, C has a parameterization. So you just use the definitions of parameterization. That's it. Now C has a parameterization. This is my parameterization. So therefore, if I change it to a contour integration, sorry, use the definition, this should be factorial n divided by twice pi I. As it is, you don't care about that. It's a constant. This should be 0 to 2 pi. This should be f of what is my z? Z is equal to z0 plus r e to the it. So therefore, z0 plus r e to the power it. Okay. Divided by z minus z0, that means r e to the power it to the power n plus 1, right? And then what is gamma prime of t, gamma or z prime of t, that means this should be I times r times e to the it dt. That absolutely you have to check, right? Now there, if I have a function, as I said, complex valued functions defined on closed interval a to b, then I can push modulus inside the integrand, but there should be lesser equal to sign. So therefore this is dominated by factorial n divided by twice pi 0 to 2 pi absolute of f of z naught plus r e to the it, keep as it is. Now this r and this r, denominator you have r to the power n plus 1, numerator you have a r, so therefore this should be r to the power n, modulus of e to the it is 1, so therefore dt. That's it. So therefore this is dominated by this object. But now this is also, I can have it. Now if t runs from 0 to 2 pi z naught plus r e to the it, it runs on the what? Contour. And on the contour, what is the absolute of f? M is the maximum. So therefore I can say that this is dominated by factorial n divided by twice pi I 0 to 2 pi. R is constant, so take outside r to the n. Now this is always dominated by m because m is the maximum of modulus of object on the contour. So therefore this is m, you can write it and you will have dt. So if I combine everything, this should be factorial n divided by twice pi. Then you have a m, you have a r to the power n, then you have a 2 pi, 2 pi, 2 pi get cancelled. So therefore n factorial m divided by r to the n, and that's what it is. Okay, so therefore it is very straightforward, I should say. If you know the Cauchy's integral formula for nth derivative, then you know the expressions of nth derivative of f at z naught in terms of contour integrations. And if I know the maximum, if I say that m is the maximum of my modulus of f on the contour, and if r is the radius of the circle centered at z naught, then you will have the estimate of this object. Okay, so this is Cauchy's estimate. Later on we will see this kind of estimate is needed to prove many theorems. For example, one of the applications of Cauchy's integral formula is the Liouville's theorem. To prove Liouville's theorem, I need what is called Cauchy's estimate, or maybe to solve some problems you need Cauchy's estimate. Okay, so yeah, so again one of the beautiful theorem which is called due to Liouville in complex analysis. This is one of my favorite theorem, I should say. It says that Liouville, I have just written something, Liouville worked on in a number of different fields in mathematics, including number theory, complex analysis, differential geometry and topology, the mathematical physics, even astronomy. He is remembered particularly for Liouville's theorem and nowadays rather basic results in complex analysis. Yes, what is the Liouville's theorem? So this is very nice. For example, so there is a, that's how kind of the it differs from real analysis to complex analysis. For example, if I say that in real analysis a function is nice means what? The function is infinitely many times differentiable, or differentiable functions, you can think about that. Now if I have a functions in real analysis, if I ask you, okay, give an example of a nice functions, you can say that's a differentiable functions or infinitely many times differentiable functions. For example, I can take f of x is equal to sin x, right? These functions. So sine functions, it's very nice functions, it is infinitely many times differentiable, it is a nice function. Cosine function, that is also a nice function, right? But what about the values of sin x and cosine x? F of x is equal to sin x, if I take the absolute, and it is always dominated by 1 for all x in R, you know. So therefore it is bounded. It is bounded, also it is nice. Nice means it is infinitely many times differentiable. But f of x is equal to sin x, if I draw a picture, it is not a constant function, right? It is very nice, it will have a graph, right? You know. Similarly, cosine function, it is also nice function, it is also bounded, but this function has a nice graph, so it is not a constant function. But what Liouville's theorem says in complex analysis is that, in complex analysis, what is my nice function? That means I have a analytic functions, or maybe I will say that analytic in the full domain or in the whole complex plane. So now, if I have analytic functions on the full complex plane, then what is the name of this kind of function? This is called entire functions, okay? So what Liouville's theorem says that if I have a entire functions f, and if you assume that your entire function is bounded, then you do not have any other choice, rather this function has to be constant. So that is the kind of beauty of complex analysis, and which clearly distinct or kind of give a distinctions between real analysis and complex analysis. In real analysis, you have plenty of nice functions like sine function, cosine functions. It is differentiable on the full real line. Infinitely many times, it is very nice functions, it is bounded, but this function is not a constant function. However, in complex analysis, if I have entire functions, or if I have analytic functions on the full complex plane, if I assume that this function is bounded on top of that, then the conclusion is that the function has to be constant, and that is due to Liouville. Okay, so as I said, why this is happening? Because as I said many times, I told you, like analyticity or differentiability, it's a very rigid property. It will be very strong rather than just differentiability. That is why this kind of conclusion is happening. So what is the statement of Liouville's theorem? So this is the statement, okay, but as I said, recall that of functions fz is said to be entire. I already said my function f is analytic at every point in the complex plane. Recall that of functions f from D subset of C is said to be bounded. Bounded means what? Yeah, I should have some number, positive number m, such that my absolute of f of z should be dominated by m for all z is in D. That is means bounded functions. By what is the statement of the Liouville's theorem? If f is entire and bounded in the complex plane, then my functions fz has to be constant. You do not have any other choice. But in real analysis, you have functions, sine function, cosine functions are there. Right, these are infinitely differentiable functions, these are bounded functions, but these are not constant. Okay, so this is one of the beautiful theorem in complex analysis, that if my function f is entire and if it is bounded, it has to be constant. You do not have any other choice. Once I have this theorem, then you can easily conclude many nice observations. For example, if you remember in my earlier lectures, I talked about if I consider these functions, f of z is equal to sine z, this kind of functions, and I gave an estimate by saying that in real analysis the sine function and cosine functions are bounded functions. However, in complex analysis the sine function, cosine functions, they are analytic functions, right? But these functions are not bounded functions. And to prove that boundedness, I assume that, or I just kind of showed you that you have the estimate, like if you remember that I have shown you that f of z modulus of sine z, and which is dominated by, I think, maybe sine hyperbolic y or x, doesn't matter, and this is blow up, this is goes to infinity as y approaches to infinity, something like that. I think I have proved it, if you remember. Okay, so that means this is one of the way to prove that a function is bounded. That means to prove that sine z is bounded, I have first established a lower bound and then say that this lower bound blows up as y approaches to infinity, so therefore your function is unbounded. Now without using that estimate, using Liouville's theorem, you can conclude that your sine functions, that means sine z function, it is actually unbounded functions. Why? Because if I take f of z is equal to sine z, and suppose you know Liouville's theorem, so what is Liouville's theorem? So if f is entire and bounded, it has to be constant, right? Now what kind of functions f? F function is sine functions, it is defined on the full complex plane, it is analytic everywhere in the complex plane, so therefore f is entire functions. First observation, f is entire functions. Now I want to conclude that this function is unbounded. So assume that f is bounded. Bounded means what? There exists m such that f of z, or you can say that such that such that f of z which is dominated by m, and this is true for all z in C, right? That is the meaning of bounded. So now f of z is equal to sine z function, which is an entire function. If I assume that it is bounded, then what is your Liouville's theorem says? That if I have a bounded entire function, it has to be constant. So therefore you are saying that f of z sine z, it is actually constant function. This is exactly equal to k for all z in C. But which is not the case. Why? Because you have a complex number and R is sitting inside C. So that means if I restrict my sine functions to R, that means it turns out that f of z is exactly equal to sine x, z is equal to x. But in that real line, sine is not a constant function, right? It is a non-constant function. So therefore this is one of the way, just using Liouville's theorem, you can conclude that your sine function has to be unbounded. Because if it is bounded, since it is entire, by Liouville's theorem it is a constant function, but which is not the case, because sine z function is a non-constant function. At least if I restrict z is equal to x, it is a sine function. In real sine function, that is not a constant function. Similarly, you can conclude that cosine z, sine hyperbolic z, cosine of hyperbolic z, all are unbounded functions in C. Just by using Liouville's theorem, you don't have to use the estimate. So there, at that time when I had I proved the estimate, I have no idea about Liouville's theorem. Now you know the Liouville's theorem. So using what is called Liouville's theorem, you can conclude many nice observations. For example, this is one of the observations. Okay, so proof, let me just go through the proof. Proof is also very nice. It is again follows from Cauchy's estimate. So what I will do, if I assume that my function is entire and bounded, I have to show that it is constant. So suppose if I prove that my derivative vanishes at each point on the complex plane, then I am done. So therefore I am considering some point z0 in C, and I will show that derivative at the point z0 is 0, then I am done. So now you see, once I have the derivative, I have to prove 0. That means I need the expression of derivative, and once I have the expression of derivative, then of course Cauchy's integral formula will come into the picture. In fact, Cauchy's estimate you know, then I am done. So it is very nice. So this is my complex plane. Take a point z0. Now I have to use Cauchy's estimate. So take a circle of radius r centered at z0. Then what is your Cauchy's estimate says? Look at the Cauchy's estimate statement. Cauchy's estimate says that if f is analytic on and inside your circle of centered z0 radius r and m is the maximum, this is the estimate we will have it. Now you see, I have an entire function which is bounded. Bounded means what by definitions? Okay, so so let z0 be an arbitrary point. We will show that derivative of z0 is 0. Now since f is bounded, so therefore you will have existence of one m such that this is dominated by m, right? Now what you do, you consider a circle. This is my CR. What is your CR? Centered at z0 radius r. So this is the circle. Now my function is bounded on the whole complex plane. So in particular it is bounded on my circle. So therefore I can say that if m is the maximum of what is called f of z, where z running over CR, this is, or if I say this is m, no. So if I say that this is say p is the maximum, so therefore you can easily say that p is always dominated by m, because m is the bound for my entire functions f. So therefore p is always dominated by m. So therefore by Cauchy's estimate, what is the Cauchy's estimate? Cauchy's estimate, if you remember, fn at z0, which is dominated by factorial n divided by m, then you will have r to the power n. Okay. So what is m? M is the maximum of my absolute of z on the contour, r is the radius, and n is the which derivative I am having the estimate. Now here I have n is equal to 1, so therefore you will have f prime of z0, which is dominated by 1 factorial times m is the maximum. Here what is my maximum? P. So therefore 1 times p divided by r to the power 1, that means r, but p is dominated by m, so that means this should be m by r, and which is this one. So therefore what you see, if I have a point z0 in the complex plane, if I consider a circle of centered z0 radius r, then using Cauchy's estimate, derivative of f at the point z0, which is dominated by m by r. Here m is fixed, but you see r is in my hand. I can take as many large r I will have. So I can take very big radius circle. So this is also true. So therefore this object is true for all r. So therefore if I take r is infinite, so if suppose I am taking r is larger and larger and larger, then what will happen? This object goes to 0 as r approaches to infinity, and this will imply that derivative has to be 0. Okay? The above inequality is true for every r, because to have the Cauchy's estimate means what? I need the analyticity on C and inside, right? And what is my C? It's a circle of centered z0 radius r. I do not have any control on r. R could be anything. So therefore this estimate is true for all r. Then I am taking r approaches to infinity. So therefore right hand side approaches to 0. So therefore f prime of z0 is 0. Z0 is arbitrary. So therefore you have derivative is 0, and therefore your function has to be constant. Okay. So this is very nice applications of Cauchy's estimate or Cauchy's integral formula for the proof of Liouville's theorem. This is one of the very beautiful theorem. Using that theorem you can easily conclude your sine z, cosine z functions, these are unbounded functions, without using the estimate. I think I should stop here. In my next lecture, that will be in week 5. There I will talk about nice consequences of Liouville's theorem. Very beautiful consequences you will see. Many problems you can solve using Liouville's theorem. So I will start with that, and then I will talk about Morera's theorem in week 5 and so on. And many more theorems, nice theorem will come. I think I should stop here. I should start in my next lecture with the consequences of Liouville's theorem in week 5. I think I should stop. Thank you.